Institute of Aeronautics and Astronautics, the Los Angeles Las Vegas section. So today we are very honored, pleasure to have Dr. Professor Ian Haworth joining us. He is an associate professor and vice chair in the Department of Pharmacology and Pharmaceutical Sciences at USC. He received his PhD in physical organic chemistry from University of Liverpool, United Kingdom, and then spent 3 years as a postdoctoral fellow at the University of Oxford, also United Kingdom, before he joined USC in 1992. His research work lies in the interfaces of chemistry, biochemistry, and computation prediction of molecular structure. This work involves development and utilization of algorithms for prediction of drug-protein molecular interaction and the simulation of ADME properties of drugs. Dr. Haworth's laboratory has published about 100 scientific articles on this work. The current project includes examining the relationship of affinity with salivation as drug-protein interfaces, prediction of ionic solubility for utilization in ADME models for prediction of drug delivery, and the use of molecular informatics in prediction of peptide delivery. Dr. Haworth also has a major role in teaching of medicine chemistry and biopharmaceutics in PharmD, which is a degree, for pharmacists, pharmacy. PharmD, PhD, and a master's program at USC, and he has lectured and taught courses on this content worldwide. He is also currently the lead co-director of the International Summer Program in the USC School of Pharmacy. Dr. Haworth has utilized problem-based learning and active learning in teaching of PharmD, of PharmD science courses for many years, and he has published and presented widely on these educational approaches. He is also interested in utilization of computational methods in evaluation of educational outcomes, including new approaches to curriculum mapping and assessment. So let's welcome Dr. Ian Haworth.
Well, thank you, Ken, and thank you everyone for attending, and most of all, thank you for inviting me to give this talk. I was really happy to do it because, as you all know, it's National Chemistry Week, and this is the first. This is the kickoff event, at least locally, and I owe my entire career to chemistry, and I've been fascinated by chemistry, quite honestly, since I was very young, and it only gets better for me. It just gets more and more exciting. I never have lost the fascination with molecules and how molecules work and the amazing things that chemists can do with molecules. And it just gets better every year. And I hope I never lose that. And I honestly don't think I will. And I really hope that I can convey that enthusiasm to you. And I try to convey it to students. And I think one of the best things for me about being a faculty member is when I see that light go on in a student and they are excited about chemistry and they're excited about molecules and they want to talk about them. And so I was really very happy to be able to give this talk. I saw that the national event has this sticking with chemistry logo, which actually refers to, I think, at the national level, a talk on adhesives, and someone's going to be talking the chemistry of adhesives. But I thought it was just good in general, and I think we've got to encourage more people and more really good students to stick with chemistry, because it'll lead to great things for them personally and for the field. So that's a little intro to chemistry in general. What I do is applied chemistry to drug design, which I'm not so much going to talk about today. I'm going to talk more about drug delivery, but really the two go together. In modern drug design, you not only have to think about the interaction of the drug with the target protein, but also how you're going to get it there, how you're going to deliver it. And I'm going to stick with just the delivery piece today, and really just what happens very much in the stomach and the small intestine, and how chemical principles matter in understanding what is happening. So I thought we should start with some molecules. And these are the 4 drugs that I'm going to mainly talk about. I don't know whether anybody would recognize them from their molecular structures. But the first one, and I'm not necessarily going to talk in this order about them, but the first one is amoxicillin. And for those of you who have children, if they ever have a infection of some sort, bacterial infection, you may remember buying some fluffy pink solution. It's actually a suspension from the pharmacy, and that's amoxicillin. And amoxicillin is very effective pediatrically, and it's also, though, an interesting drug from a delivery perspective. And I'll say a little bit about this actually towards the end of the talk, about how fortuitous it is that amoxicillin and other penicillins, because amoxicillin is one of the penicillins, its delivery properties are very fortunate in terms of the original discovery of penicillin. So we'll get to that eventually. Here's ibuprofen, and you've probably all taken ibuprofen, Motrin, or Advil in your life for pain, for headache, for joint pain, that kind of problem. And some people ibuprofen works great, and you get relief. I'm happy to say I'm one of those people. Ibuprofen really works well for me. Other people take ibuprofen, they don't get relief, or it takes a long time. And it's almost folklore that people will say, you know, oh, why doesn't it work for me? Well, there are really good reasons for that, and I'll explain some of them. They have a lot to do with the chemistry of ibuprofen and the nature of the way that it's made in a tablet. Then itraconazole. So itraconazole is perhaps a drug that you might be less familiar with. It's an antifungal agent. And it really is the worst nightmare of someone who is trying to deliver a drug. This is a really difficult drug to deliver. And I'll explain why. This drug has been around for 30, 40 years. It's generated a huge amount of literature in terms of improving its delivery. Some fascinating chemistry, but it's still difficult to deliver. And then here's a newer drug. For contrast, this is sitagliptin. Sitagliptin is a diabetes, an anti-diabetes agent. And it really is a beautifully designed drug. It's newer. It was designed based on a lot more knowledge of drug delivery, and it works just great. And it's a perfect drug in terms of its delivery. So we'll talk about all 4 of those as we go through here. So first thing we'll start with is something not very chemical, which is the gastrointestinal tract. And but we got to talk about the gastrointestinal tract a little bit, because all of this delivery process is happening there. So the tablet appears in the stomach, and it's going to dissolve in the stomach. We'll get into that a little more in a moment. And then the dissolved drug is going to go into the duodenum and the jejunum. This is the small intestine, and that's almost completely where the drug is going to absorb into the blood. So that's really all you got to remember here. Dissolve in the stomach, and then move into the duodenum and jejunum, and this is where the process of absorption into the blood occurs from. And the other thing to remember is that the pH of the stomach is low. In a fasted state, very low, somewhere around 2. in a fed state, a little higher, 4, maybe 5. Um, and so, but then once the drug encounters the small intestine, pH goes up to about 6 and even as high as 7 and eventually 8 in the colon. But there's not a lot of drug absorption from the colon. But the point is the drug is encountering lots of pHs as it goes on its journey through the gastrointestinal tract. And of course, that is important if the drug is ionizable, because the ratio of the ionic to neutral form is going to change. And that's certainly one chemical principle that's very important in drug delivery. Here's a little bit more detail of that. So, and now from a more chemical point of view, oral administration of a tablet into the stomach. Won't talk about this very much, but the tablet has to break apart. It has to disintegrate, and it disintegrates to release drug particles. Here's a under the microscope, a larger version of the drug particle, and a still larger version. So here's the edge of the solid particle of drugs. We can now start to see the molecules in the solid particle. The arrangement of these molecules is very important. It could be crystalline, could be amorphous, and I'll talk a little bit more about engineering of crystal forms of drugs, which makes a big difference in terms of what's going to happen next. We're still in the stomach at this point. The drug starts to dissolve, and it will establish an equilibrium. And that equilibrium is going to depend on the pKa of the drug. And it's going to be an equilibrium broadly between a neutral form and an ionic form. And the position of that equilibrium is important. As we'll see, because we need some neutral form. How much? Not necessarily all that much, maybe 1%, even a little less, because the neutral form is going to then, after we move to the small intestine, so this dissolution process is occurring in the stomach, but once dissolved, the molecules are going to move into the small intestine. This equilibrium position is going to shift, but we're still going to have an equilibrium, and we need a small amount of this neutral form, and it's going to diffuse and then partition between the small intestine, which is still essentially aqueous, and what we'll call the lipid barrier. It's really a cellular barrier, but the lipid barrier between the small intestine and the blood. And so this is a partitioning event controlled by an equilibrium only for the neutral form. And this is the log of the partition coefficient. And the equilibrium is set up here, and the same thing here into the blood, which we again consider aqueous. This whole equilibrium system would be established, and nothing would happen except for one thing: the blood, we hope, is flowing. And the blood flow takes this molecule away, disturbs this equilibrium position, pushes another molecule in, which disturbs this one. Molecule goes into the lipid barrier, which disturbs this ionic to neutral equilibrium. An ion is converted to a neutral form of the drug, and the whole process continues. Now, and this is what drives the drug across the lipid barrier. Now, the problem here, though, is that there's only a certain amount of time for this to happen. And in terms of dissolution in the stomach, maybe 30 minutes, maybe a little more, something like that. And then in terms of periods spent in the small intestine, maybe 3 hours. So overall, perhaps a total time of about 4 hours for this to happen. That's called the transit time. And so if we're going to get our drug absorbed, pretty much it's got to happen in 4 hours. If it doesn't happen in 4 hours, you've really lost the drug in the tablet, what's remaining. It's not much of it is going to absorb after that. And so this time limitation is important. It means that we've got to have a drug that dissolves fairly quickly, but once it dissolves, we've also got to have a drug of which the neutral form will partition fairly quickly and cross this barrier. And there are other factors that can affect that. And one thing I'll talk about is the effect of food. Of course, this is the intestine. There's food there, the patient's eaten. And the food can actually have really significant effects on the ability of the drug, first to dissolve, can actually improve the dissolution, but also to partition. And so this becomes important. The environmental conditions of the intestine are going to have an effect. So here's the very early, by which I mean the 1990s, way of trying to think about, well, what are the properties of a drug that help it absorb after it's taken orally? So this is a very famous rule in pharmaceutics and biopharmaceutics, the Lipinski rule of 5. And Lipinski said molecular weight's got to be less than 500. We want less than 10 hydrogen bond acceptors. We want less than or equal to 5 hydrogen bond donors. And the log P, and the log P being a measure of hydrophobicity. So a drug with log P 0 is part hydrophilic, part hydrophobic. As log P becomes more and more positive, the drug becomes more and more hydrophobic. We don't want to go over 5 in the Lipinski rule. And then in addition, this is not the original Lipinski rule, but in addition to the Lipinski rule is we don't want the molecules to be too flexible. So we don't want too many rotatable bonds. But so these are the basic properties. If you look at groups of molecules, they actually work pretty nicely. This is a big data set. We'll get into this in too much detail, but what this number is the bioavailability, F. And the bioavailability basically is a measure the percentage of the original dose that reaches the blood. So you want this number to be high. You want high bioavailability. And if you look at this set of data, the drugs with high bioavailability fit better into the Lipinski formulation. And so the Lipinski rule has been very useful for pharmaceutical scientists in terms of understanding the kinds of molecules that will make good drugs. I might say that it also has been a little bit restrictive in the sense that molecules that break Lipinski rules tend to be thrown away quite quickly. And that maybe means that some potentially good drugs have been lost, and it may have taken a little more effort to deliver them, but they otherwise would have been good. And this is increasingly, I think, a problem in the field, that Lipinski has been the way people think about this for many years. But the kinds of molecules that are being made at the moment, many of them do break the Lipinski rule of 5, and but it may be necessary for the sorts of targets that we're looking at the moment. But that's the way that people think about it, and this is still currently, very much currently used. And if you want to play with the Lipinski rule of 5, you can go to this website, More Inspiration, and you can put in what's called a smile string. This is a representation of a molecule. You can get smile strings from PubChem, and just paste in the smile string, and it gives you these Lipinski properties. And this is omeprazole, which is a proton pump inhibitor. So this is a nice way to play with this and learn a little more about the Lipinski rule of 5. So now, but you've got to think a little beyond Lipinski in terms of really trying to understand what makes a drug work, what makes it orally deliverable. And so here is sitagliptin. So this is the structure of sitagliptin, and sitagliptin, as I said at the beginning, is an anti-diabetes agent. It actually helps to maintain secretion of insulin in a patient with diabetes, and that contributes to homeostasis of glucose. And sitagliptin is a very effective drug. It's one of the best diabetes drugs on the market at the moment. It's called Januvia, its trade name, and so this is sitagliptin in its basic protonated form, with an NH3 plus here, and NH2, and the PK is 7.7. So this is already a useful property, because it means that sitagliptin is largely going to be protonated at lower pHs. And that is advantageous because if you look at the rate of solution, so one of the things we're interested in here is how fast does this molecule get into a solution? At pH 1.2, it gets into solution very quickly. You can see after only about 10 minutes, maybe 20 minutes, it's pretty much dissolved. And that's great, because that's the kind of time we've got in the stomach for dissolution. So sitagliptin, we know, is going to dissolve very well in the stomach. But its pK is 7.7, so as it moves into the small intestine, this equilibrium is going to shift from blue to red, and we're going to have more of the neutral form, still overall more of the ionized form, but the percentage present of the red form, the neutral form, is going to increase. And when we get to about pH 6, we're going to have 1 to 5% of this red form, and that's also really good for two reasons. One, that the solubility of sitagliptin, and this is shown here, pH versus solubility, around about 6 is still quite high. Even at 7, it's quite high. So we have no problems with solubility, but we have quite a lot of the neutral form, and the log P of the neutral form is 2, which means that it's hydrophobic enough to move into the gut wall. So this drug works beautifully. It dissolves fine in the stomach. It moves to the small intestine. It's still soluble, but there's enough of the neutral form to partition into the gut wall and drive that process. And the net result of that is sitagliptin has, from memory, 87% bioavailability, which means that 87% of the original dose reaches the blood. And there is a little bit of loss. I won't get into why that is. It happens more once the drug has actually reached the blood, because bioavailability is a slightly more complicated definition than I'm giving you. But basically, the whole dose of sitagliptin is getting into the blood, and that's good news. The other thing then about sitagliptin, so this is the other curve that I wanted to talk about. This is a time post-dose versus plasma concentration plot. So this is how much drug is actually in the blood. And there's an absorption phase and then an elimination phase. And one of the things that is always important in looking at these kind of data for a drug is, does food affect that behavior? So here's sitagliptin. We've got in the fed state, is here, it's a little hard to see, but this is the fed state. This is the fasted state. They're different, but not very different. And so the conclusion is it really doesn't matter. Januvia, sitagliptin can be taken with or without food. So there's no problem there. The patient doesn't have to worry about whether they've eaten or not before they take their Januvia tablet. And everything works nicely. This is a great example of a drug that behaves very nicely. Now, Here is a slightly different case. So this is ibuprofen, and as I said at the beginning, some people are very responsive to ibuprofen, others less so. And there's also a fairly new form of ibuprofen, which is called fast-action Advil. And you might look at that and think this is a marketing tool. It doesn't mean anything, but actually it does. And fast-action Advil, as I'll tell you, is really due to a chemistry change in the way the ibuprofen is formulated. So let's look at some data here. First of all, this is again a time versus plasma concentration, and what you can see here are actually 3 formulations of ibuprofen. We'll just look at the ibuprofen sodium and standard ibuprofen. Ibuprofen sodium is this curve here. And what this shows is ibuprofen sodium is getting into the blood very quickly and reaching a peak after probably 1 hour or so, actually less than 1 hour, probably 45 minutes. On the other hand, standard ibuprofen, which is just regular ibuprofen, just this molecule, reaches and enters the blood much more slowly. It takes close to 2 hours to reach a peak, and the peak is lower. So you can see that ibuprofen sodium really does have faster onset. And this is, in fact, what is in Advil rapid onset or Advil fast onset. And so ibuprofen sodium is a salt with a carboxylate ion, anion, and a Na plus cation. And because of that property, it has greatly enhanced dissolution. So the dissolution rate is much faster. It gets into solution much faster. Once it's in solution, it equilibrates. There's really no difference once ibuprofen sodium and standard ibuprofen have dissolved. They equilibrate with respect to the local pH, and there's a certain percentage of neutral and a certain percentage of ionic ibuprofen, and then the partitioning process and movement through the gut wall occur. The key is getting the ibuprofen into solution, and the ibuprofen sodium formulation really does that much more effectively. So this fast onset is real, and it's due to a chemical change in the way the ibuprofen is presented in the tablet. Now, the other thing, though, here, and this looks like a real mess. It's actually pretty interesting because what these data over here are averages over a population. They look very clean. But when you look at individuals, you see very different results. So the Tmax is the time to reach the peak concentration. So I was trying to read off the graph here, but we've got some numbers here. For ibuprofen sodium, it's 35 minutes. So it takes 35 minutes to reach this peak concentration after dosing. On the other hand, for standard ibuprofen, it turns out, if you analyze this curve, it's 90 minutes. So it's almost 3 times as long. And that's obviously why you have a rapid action, you have a fast onset. But if you look at individuals, each one of these lines is for an individual, and you can see that most of them go up. Most of them go up. So if we look at this person here, their Tmax with ibuprofen sodium is here. Their Tmax with ibuprofen, standard ibuprofen, is here. So it went up, which is consistent with the general population behavior. But then this individual had exactly the opposite effect. Tmax is actually higher with sodium, ibuprofen sodium compared to standard ibuprofen. There's another individual here that happens. And so this kind of population plot is representative of an average, but the average doesn't necessarily apply that well, even to most individuals, and certainly not to some. And so there's something about the physiology, and it probably is physiology here, of certain individuals that set them apart from the population. And these are the people who would be saying, well, that fast onset Advil is useless. It doesn't work. I'd rather take the normal stuff. But most people would have a benefit. And you see these kind of data in lots of drug studies, individual differences, even though the population averages look very clean, but the individual differences are quite significant. Now, let's take this just one step further, because ibuprofen also depends on the presence of food. And so here now we've got in green standard ibuprofen delivered in a fasted state, that's the green line, and a fed state, which is the black line. And you can see that now there's a further delay. So we had a delay from ibuprofen sodium to standard ibuprofen, but now if we take standard ibuprofen in a fed state, we're not talking about 90 minutes for Tmax, we're talking about perhaps 5 hours. So the population average there is 5 hours. And now that doesn't mean that you don't get an analgesic effect before 5 hours, because there may be enough drug for that to occur much earlier. But the peak concentration isn't reached until 5 hours. This study, which was from the University of Michigan, was a really fascinating study, and I'll just summarize it without getting into all the details. There's a rather unpleasant study as well, because what they did is they pushed a device down people's throat all the way into their small intestine, and they were able to measure pH levels and drug levels all the way down. And they kind of say in the abstract to this study, they say that 23 people started the study and only 11 came back the next week. And there's a certain deadpan humor to that, because it's kind of surprising that even anybody came back. But those people really, the subjects of the study really gave us some beautiful data, because what is basically being shown here is, and just look at the blue line. The blue line is the amount of ibuprofen in the stomach under fasted and fed conditions. And you can see that under fasted conditions, it only barely gets above this 10,000 mark, and we won't worry about the units, but whereas, and this is a log plot, in the fed condition, it gets above 100,000, and so it's about a 10 times difference just in the first half an hour or so after dosing, and then it comes down, and after about 3 hours it's about the same. But there's this quite long period where ibuprofen, if taken with food, it's trapped in the stomach, and it can't absorb in the stomach. It doesn't absorb, so nothing can happen. And so the food is actually restricting the access of the ibuprofen to the small intestine. The stomach motility is reduced in the presence of food, and that's the reason why you get this delay. So this is not so much a chemical issue now as a physiological issue. And again, if you go to individuals, and a lot of data kind of complicated here, but each color is a different individual. And you see some individuals don't reach a peak until maybe 8 hours. So these people really are not going to feel an effect of ibuprofen, and they're taking it for a headache, but they don't get any relief for hours and hours and hours. So they go on and choose some other analgesic. So the bottom line of all this being then that the environment of the GI tract is very important. The chemistry of the molecule is very important. The physiology of the individual is very important. And all of those conspire to give onset of the same molecule, the same drug, that can vary from within half an hour to up to maybe 8 hours in certain individuals. And unraveling all of that is really crucial in understanding oral delivery. So now here's itraconazole, and this really is a very difficult drug to deliver. And the reason is that it's got extraordinarily low solubility, 1 nanogram per milliliter at pH 7, 4 micrograms per milliliter at pH 1. A little better at pH 1 because it gets protonated, but still very low solubility. You can do things to itraconazole. These blue curves are dissolution rates of the salt and the neutral form. It doesn't really work with either. We're getting very little drug in solution after 30 minutes. So that's pretty hopeless. This molecule is beta-cyclodextrin, and beta-cyclodextrin is very interesting. They're hydrophilic on the outside and hydrophobic on the inside. If you mix beta-cyclodextrin and itraconazole, the itraconazole goes straight into the middle of the beta-cyclodextrin. And if you look at the rate of solution, which is shown here, of that complex, it really gets into solution very quickly. And so there are beta-cyclodextrin itraconazole formulations that actually work in exactly that way. That's how itraconazole is dragged into the solution of the in the GI tract. Now, the other thing though is that itraconazole actually works better with food because the food has a similar effect. It's not cyclodextrin, but it's lipids in the food that do the same thing. They help the itraconazole dissolve. And so itraconazole has to be taken with food. You can see a much higher peak itraconazole with food compared to without food. And the amount of itraconazole that reaches the blood, if the patient hasn't eaten before they take it, is much, much lower than if the patient's eaten some food. And so this is very important. Very important, but also somewhat of a problem because the patient has to remember that they've got to eat before they take their tablet, and that might be difficult to remember, or people forget. And so there have been lots of attempts to modify itraconazole, and this has been an active research area. You see, this paper, this was published in 1989, so this is now 30 years ago. So this basic idea has been well understood, but the question is how you do something about it. What can you do? This is a much more, and I forgot to put the reference on this paper, but this is on this slide. But this is a very recent paper where the itraconazole has been engineered in the solid state, and this is a pretty nice example of manipulation of the solid state of a drug to improve its rate of solution. And again, the problem being that if it doesn't dissolve quickly, then it doesn't have time to absorb into the blood. So here's itraconazole again, and this is an image from the solid state itraconazole structure. And the key point here is you see that these two aromatic rings are lining up, one here and one here. And this piperazine in the middle is sort of lining up on top of each other. Very hydrophobic interface. And this is one of the reasons why itraconazole is so insoluble and and has such a slow rate of solution, because this hydrophobic surface is sticking together in the solid state, and it really just won't come apart. That's also why if you put a lipid into the solution from food, it starts to break apart, because this offers a different hydrophobic surface for the itraconazole to bind to. But that again is dependent on food. And so the question is, can you do anything about this? So what was done here is construction of an itraconazole succinic acid co-crystal. It's remiss of me not to indicate the authors here, because this is a very nice piece of work. So here's succinic acid, and this is the crystal that was produced. And now what you see is these two triazoles have folded inside from, and shown in schematic here. Here's the succinic acid. It's not charged, by the way, it's neutral. But now, beautifully, the succinic acid has split up these hydrophobic faces of the itraconazole. And so we don't have the same problem. We don't have this stickiness, this hydrophobic stickiness. And look what happens. Here's the dissolution profile. Here's itraconazole. We get maybe 25, 30 micrograms of itraconazole dissolving after 30 minutes. But if this is regular itraconazole, if we look at the succinic acid co-crystal, then we get 200 micrograms. So maybe the order of 7 or 8 times increase. And if you go back to here, this is roughly the same kind of increase that we got by including cyclodextrin. So this is a beautiful engineered crystal, and it's not used clinically yet, but this is the kind, and there may be other reasons that it wouldn't work, but certainly in terms of dissolution, it works perfectly. And this is, again, an example of using chemistry to manipulate the behavior of a drug. Now, I will just say one other thing here, and this is a drug I didn't mention at the beginning, but rufinamide. Rufinamide is a drug that's actually used. It's an anticonvulsant. It's used in epilepsy, and it's the kind of drug that really throws you, because when I look at rufinamide, I see a nice hydrophilic part, a little bit of hydrophobicity. Looks like it should behave beautifully. It should dissolve fine. Should partition fine, and you don't expect any problems. But actually, turns out the rufinamide is massively influenced by food, and it's surprising that if rufinamide is taken without food, it has much lower plasma levels than if it's taken with food. So it's a little bit like itraconazole, and yet it doesn't look anything like itraconazole in terms of its chemical properties. Turns out that it's the same kind of problem. This is the rufinamide X-ray structure, and without getting into too many details, you can see the aromatic rings form this beautiful stacked structure, and there are also some hydrogen bonds between the molecules. But this aromatic ring stacking is really, really stable, and hydrophobic stacking is hard to break. And so rufinamide doesn't dissolve very well. And without getting into the details here, you need food, you need something to induce the dissolution. And when you have that food, you see you get a much, much higher concentration of rufinamide in solution. So sometimes you can look at a single molecular structure and think one thing, but when you see what's happening in the solid state, It's really quite a different story. So finally, I'll just say for a couple of minutes, I'll talk about amoxicillin. And amoxicillin, this is amoxicillin, and like all penicillins, amoxicillin has this beta-lactam ring. And when you look at amoxicillin, and indeed most penicillins, from a perspective of oral absorption, you really wonder why it works, because amoxicillin is extremely hydrophilic. You can see all these hydrogen bonding groups, and something that's that hydrophilic, it's going to dissolve fine. There's going to be no problem with it dissolving, but then it's not going to permeate. It's not going to move into the lipid barrier at all well, and so. But having said that, amoxicillin is given orally, it works fine, so does penicillin. And of course, it was discovered as an oral drug and as an oral entity. And so it just turns out fortuitously that amoxicillin and other penicillins do not absorb passively through the gut wall. Instead, they're substrates for proteins that are in the gut wall. And this is one of those proteins, H-peptide-1, the human dipeptide transporter, that I've personally done a lot of work on, and a lot of work has been done at USC. And human dipeptide transporter is present physiologically to transport dipeptides. Here's a dipeptide, ALA, and it works well for those. Turns out, though, that amoxicillin will mimic, because it's got a NH3 plus and a CO minus, same as a dipeptide, it mimics the dipeptide. And it's a substrate for this transporter. And it moves through the transporter from the gut, which will be this side, and through into the gut wall and eventually into the blood. And so I just threw this example in because it is important to recognize that not all drugs absorb passively. Some of them use proteins to transverse the gut wall, and fortuitously, the penicillins are in that category. If they were not, they would be orally useless, basically. They would not absorb passively, or only to a very small extent. So let me just finish off by saying that again, I was very happy to be asked to give this talk, and one of the reasons I actually thought of giving the talk was we published a paper fairly recently, just early this year, in the Journal of Chemical Education, and this is a little bit of a different focus, but it includes all the things that I've talked about today. It's actually also using software to simulate these properties, but you can see the properties that we were simulating were pKa's and log P and various solubilities. And here's a plasma concentration, time versus concentration curve. And here are some rates of dissolution. So these are all the things that I've been discussing today. And so we sent this to the Journal of Chemical Education. And one of the questions that came back, and a very reasonable question from the editor and the reviewers, was, well, should this really be in a chemistry journal? And is this suitable for an undergraduate chemistry curriculum? And I thought it was a very fair question, and we sort of ignored it in the paper because I think we, in writing it, assumed, well, yes, the answer is yes. But they really forced us to think about that, and in the revision of the paper to put in the reasons why this is very suitable for undergraduate chemistry teaching, and it definitely improved the paper. It made me realize, just how many chemical principles, physical chemical principles we're getting at in thinking about drug delivery. And And so that was I was very grateful for the editor for pushing us on that issue before before the paper was published. So let me just wrap up here. What do we need for good oral absorption? We need a mixture of hydrophilic and hydrophobic properties. Hydrophilic, get the drug in solution. Hydrophobic, partition into the membrane and into the gut wall and move into the blood. Can we use physical chemical data from in vitro experiments to predict drug delivery in vivo? Yes, I think you can. You have to be careful, but basically you can certainly get a lot of information from very fundamental physical chemical properties regarding how the drug is going to behave in vivo. On the other hand, we've also got to take into account that this is in vivo. It's not in the test tube, and there's physiology and anatomy to be concerned about. And one of the fun things in this field is you really do have to learn more than just the chemistry. You really have to understand that environment biologically. Back to chemistry though, the solid state form of the drug really matters here. It's overlooked a lot of the time, but actually it really matters, and you can influence the extent of delivery with a nice form in the solid state. And then finally, and this is part of the point of the paper I just mentioned, that there's ever increasing models of ever increasing sophistication that allow you to simulate drug delivery based on physical chemical data, and I have to add biochemical data, because once the drug gets in the blood, and we've not thought about that at all, but once the drug gets in the blood, it's subject to metabolism, it's subject to interaction with other proteins, including other transporters, and all those data are really important in actually generating the final plasma versus plasma concentration versus time curve. So I hope I've convinced you that chemistry is very important in drug delivery, and that this is a great field for people who are interested in chemistry to apply their chemistry to a really important area, which is improvement of old drugs and design of new drugs. So with that, I'll finish, and if there are any questions, I'd be happy to answer them. Thank you.
Yeah, thank you so much.
Thank you.
This is wonderful. Is anybody has any question? You are welcome to unmute yourself and turn on your camera and say something, ask some question.
Dr. Haworth, this is Krishna Kalluri.
Hello, yes.
Does a human serum albumin play any part in drug transportation?
Yes, it does. A big part, and of course the albumin is in the plasma, and so once the drug gets in the blood, some drugs are 99% bound to serum albumin. So as they move around the systemic circulation, they're not moving in the free state. They're moving bound to the albumin, and that doesn't destroy the drug in any way, but what it does do is it stops it being eliminated. It also stops it being active as well. It can't reach its active tissue, so it basically just slows down the rate at which the drug works. So the drug is in equilibrium with the albumin. There's always a small amount free, and that small amount will move into the target tissue or perhaps be eliminated. But yes, albumin is crucial in this is referred to as protein binding, by the way. The generic term is protein binding, but it's a measure of the extent of binding to the albumin. Very important. Yeah, great question.
Thank you.
I had a question, if I may.
Yes.
So as an organic chemist, I often justify my kind of methodology research to see I justify it by saying like, oh, well, you know, these molecules could be used in drug discovery, but I don't actually do any of that. So it's
Right,
kind
right.
of, it stops there for us. But what would be the kind of the first step or the easiest thing we could do to further justify that claim? Like, would it be useful extra data on our end to give like some kind of solubility test information, or I don't know, what would be the kind of the easiest step for us to take?
Yeah, no, that's a really good question, because I understand that you know, a lot of people would like to, for all sorts of reasons, provide evidence that the molecules you're making could actually be drugs, or at least have a reasonable chance. So assuming that they have some kind of activity, obviously, that you know, against some enzyme, which is an entirely different issue, but I think it's really important, first of all, just to show that you're thinking about delivery. The history of drug design has been such that 30 years ago, the designers and the deliverers didn't talk to each other at all. And so the people who come up with good molecules that were good inhibitors of enzymes in the particular disease state, but then they were almost impossible to deliver because there'd been no thought about the delivery. So just thinking about it is a good start. But then, yeah, what could you do that's a little more concrete than that? I think applying Lipinski's rule of 5 would be good, just to get a quick measure of the suitability of the drug. I think that's a little dangerous though, because as I said in the lecture, that there is a little bit of a limitation with Lipinski's rule, particularly for newer molecules and newer targets. So simulation is really important, and actually you mentioned measuring solubility, and that is a, you know, it's seemingly a very simple parameter to measure, but actually having a good solubility, a good piece of solubility data can really help with the simulation. And I've found this a lot, that predicted solubilities are not still that good, particularly ionic solubilities, and so if you're beginning to go down that road towards understanding whether a new molecule is going to be deliverable, I think first of all, putting it in a simulation is interesting, just purely based on its molecular structure, letting the simulation just calculate everything, and it can be done. But the results there can be really helped by one or two well-characterized physical-chemical parameters like solubility, maybe log P, things that are really critical in the simulation. And the simulations work by utilizing as much experimental data as possible. So just a small amount of experimental data can be really helpful.
Yeah, thank you. I think that's a good place to start. And I really appreciate your talk. It's been very helpful. Yeah, coming from that side of it. I mean, I don't normally see any of this any of this connected to actual chemistry. Usually everybody talks about it in a very narrow context, and this has helped me kind of see it in a broader kind of view, and that's very helpful for me for writing justifications for my chemistry.
Absolutely, and that's great, and that's what I was hoping to do, because I agree. It's always difficult. You're making molecules. You've got to justify why you're doing it, and I think just a little bit of this can actually go quite a long way. Yeah.
Thank you.
Great.
Question, you're welcome to unmute yourself and turn on your camera to speak.
Yeah, Dr. Haworth, this is Krishna Kalluri again. I just wanted to find out, supposing there are two drugs administered at the same time, will one have an effect on the other?
Yeah, no, another good question, and I you know, these are beautiful questions, and I restricted this talk to basically what happens in the stomach and the GI tract, because there's plenty to talk about there. There's even more to talk about once a drug gets to the blood. One of them is the albumin issue. The other one is another one is exactly that. What happens if you deliver two drugs at the same time? And the term that's used in pharmacy is there a drug-drug interaction? Now, that doesn't mean that's not a chemical interaction per se. So it's not a molecular interaction between the two drugs. It's does one drug affect the pharmacokinetics of the other drug? In other words, does one drug change the rate at which the other drug is eliminated, for example? And that's quite common. So if you think of a good example, for example, statins. Statins are cholesterol-lowering agents. They're eliminated hepatically, so they're eliminated through the liver. They get metabolized in the liver, but they get into the liver using a protein transporter into hepatocytes in the liver using a protein transporter. If you give a statin with another drug that blocks entry of the statin into the hepatocyte, in other words, is an inhibitor of that protein transporter, then the statin stays in the blood, number one, because it doesn't get eliminated. And number two, which is an even bigger problem, it then starts to reach other tissues. And the net result of that is some pretty bad adverse effects. So the answer is definitely yes, drugs can influence each other. Not all drugs do, but some drugs have really quite serious drug-drug interactions that cause. I mean, even in the worst possible case, they could even be fatal. But that would be the consequence of a very bad mistake. But in general, they would just cause adverse effects, or they would reduce the efficacy of one of the drugs. Yeah. And this is a big area, and another area of great interest to me of how you predict that, how you predict that kind of behavior. Again, using in vitro data to try to predict what's going to happen in vivo. But that's more biochemical data. That's inhibition of proteins, inhibition of metabolizing enzymes and protein transporters and the like. This is a great area.
Thank you very much. And as an executive committee member of the local American Chemical Society Southern California section, I sincerely thank you for a great presentation.
Thank you very much.
And I'm sure all of our colleagues, the executive members as well as the regular members of SCALAX have enjoyed the presentation very much. Thank you very much.
Thank you.
Yeah, actually, I was an ACS member like 12 years ago. You know, at that time, my work involved some of the chemistry. Also, it's not exactly drug, but it's helping drug development at that time. So I joined ACS for a few years, but later, of course, it's my work is not related anymore. So sorry, I discontinued. Actually, I do have because in your slide you mentioned Linus Pauling Institute. You part of your slide. I think you referred to Linus Pauling. Yeah, I think one of the. I don't remember. I think the earlier slide you mentioned Linus Pauling Institute.
Ooh. Where was this?
Maybe it's just a reference, but I somehow catch it.
Maybe it's just a reference.
Yeah, it's somewhere there's a reference to.
I don't know where that would be.
Well, I
But go ahead. Yeah.
But anyway, I recall, when we in college, actually I studied the Linus Pauling, this general chemistry, it's a textbook,
Yes.
and I kind of fascinated, this because you talk about you doing computational,
Yes.
method. Are you referring to those things, that involving those orbital, like a 3p, those kind of quantum mechanic calculation?
Right, yeah. Well, actually, I have done those kind of calculations a long time ago. Most of the things we do are not really at that kind of level of theory because we're actually trying to do not so much there's not quantum chemistry because we're trying to instead deal with um, simulation on two levels. One is literally simulating based on parameters, based on properties, based on equilibria. So we have simulation models that use equilibria and then we try and analyze the positions, the equilibria, and how that drives the dissolution process. And then on the other hand, one of the things we're also trying to do is actually look at the molecular basis of, for example, one, and again, I didn't talk about this because this is a post-absorption process, but exactly how molecules interact with metabolizing enzymes it's known. I mean, there's no question about that. There are lots of X-ray structures, but in terms of predicting whether a molecule really will be metabolized, the extent to which it be metabolized, the position on the molecule that will be metabolized, that will be chemically altered, all those questions are still pretty open and very hard to predict without using some kind of molecular model. So there we are using molecular modeling, but not at that kind of high quantum theory level, but more with a force field approach, where you're trying to mimic molecular association. So there's the research that I'm most interested in at the moment actually is to try to bring together sort of molecular level representation with pure mathematical simulation that uses parameters such as log P, ionization, pKa's, and then once you get into the biochemical end, IC50s for inhibition of enzymes, KIs, KMs, Vmaxes, the normal kind of biochemical parameters. So trying to bring those two together so that you can use those parameters, but you also can basically predict them in a way at the molecular level, which is a little bit different to quantum chemistry. Because it basically because it's too slow for us. We need to do it more quickly than those kind of calculations, which are detailed and take a while.
Yeah, understood. And how about do you often need to resort to X-ray, crystallography,
Yes.
and NMR and nuclear magnetic resonance study? How often, what is? Yeah.
I personally don't do. I actually did a lot of NMR earlier in my career, and I don't do that anymore, and or I don't personally do X-ray, but certainly the data from X-ray crystallography, as I showed for the small molecules, but also data for drugs binding to binding metabolizing enzymes, and increasingly binding to transporters. This is still an area that really biophysically has not been solved. There's still very few structures of human protein transporters, and which is very limiting in terms of understanding how they work, and predicting whether a given drug molecule will be transported. It's still a difficult area. We in the PepT1 data that I showed you very briefly. This protein was first cloned, I think, in 1994, and it was really a panacea at the time. It was thought that, well, you just tag a drug with a dipeptide, and it should interact with this transporter, and the dipeptide will take the drug across, and then we release the drug somehow, and everything's good. That's not panned out, and part of the problem is that there's still no X-ray structure of the full human transporter. It's very hard to express. It's really hard to crystallize, and so mechanistically, we still don't really know how it works. There are some bacterial analogs that help, but they don't really get there. So yeah, this is a field that really does need biophysical structures, and because once you have the biophysical structure, you really have a good chance at that point then of understanding at a molecular level how drugs are going to interact with that structure, and doing something predictive.
Yeah, completely agree. When you show this slide, I immediately come to two things. One is, you're using the peptide transporter, but I immediately, because the picture, it kind of remind me this calcium channel, for like that's the calcium pump. Sometimes there's probably some kind of delivery, like using that process.
Yeah, and this is, I didn't have much time to talk about all the details here, but this is proton driven, so it uses the proton gradient from the intestine to the blood to drive the process. And there are models, and I've developed a model, but I'm not, frankly, that convinced that it's right. It's the idea here, and I didn't get into this much, but the idea here is that there's some kind of pharmacophore, the distance between the amine and the acid is important, and it probably is. But actually, I could show you many molecules that don't have an amino terminus or an acid terminus, or at least only have one or the other, and there are some that don't have either, and they still go through this transporter. So, the understanding is still weak in terms of what really makes a drug move through a transporter, and it's not just HPEP-1. There's many other transporters, and there are specific anion transporters that people have shown that cations go through. So there's all sorts of difficult issues there that are very restrictive in terms of prediction, because you try to predict how a drug might interact with a particular transporter, but actually it's really, really difficult to do. And yet it may be the key to the absorption of the drug or the elimination of the drug. So there's a lot that's not known there. There's a lot that is known as well, I have to say, but there's a lot that's not known.
Yeah, I agree. There's lots of fun. A lot of things, even the daily thing, the ibuprofen, Tylenol. There's a lot of chemistry. Lots of fun.
Yeah, and there's, I honestly could give this talk 10 times over on different drugs, and there's all sorts of interesting stuff that can be talked about. And
yeah, there's so many. Yeah, there's I can see great potential. There's lots of things you can talk about. Yeah.